Okay, hello everyone. Let's go ahead and take a look at monotonic sequences. And what we're again trying to determine is whether or not a sequence is diverging or converging as we take larger and larger values of the sequence. Now let's go ahead and define first of all what a monotonic sequence is. It says a sequence is monotonic if a sub n is less than or equal to a sub n plus 1, or a sub n is greater than or equal to a sub n plus 1 for all positive values of n. Now what I have here is I have the situations for both of these graphed on these particular two graphs. And in this particular case, this is going to be for all the cases where a sub n is less than or equal to a sub n plus 1. So in other words, if I was to go ahead and take a look at, just say for example, this green particular sequence, okay, and again, the values that we're talking about are only these values. The only reason why I have the dotted lines is just so that we can kind of see the progression a little bit easier. If I go ahead and take a look at a sub 1, then a sub 2 is of course going to be larger than that. If I take a look at a sub 2, a sub 3 of course is always going to be larger for that. And that would be the same even for the red, because if I go ahead and take a look at a sub 1 is going to be less than a sub 2, which is less than a sub 3, which is less than a sub 4, etc. Now, if I go ahead and take a look at the second situation here, where a sub n is always going to be greater than or equal to a sub n plus 1, then notice that a sub 1 is always going to be greater than a sub 2, is always going to be greater than a sub 3, is always greater than n sub 4, etc. And even in this case over here, a sub 1 is greater than a sub 2, which is greater than a sub 3, which is greater than a sub 4. And that would also work for the black dots representing the sequence here and here. Now what we're going to say is that this particular sequence, all three of these are going to be considered monotonic increasing because it holds this property true for all positive values of n. In this case over here, it is going to be monotonic decreasing. Now I'm hoping that everybody remembers when we came across this idea of monotonic, and that came across when we dealt with functions and we were looking at whether or not a function is increasing or decreasing over its entire interval. And we talked about monotonic increasing functions and monotonic decreasing functions when we looked at the derivative. So we can actually go ahead and determine whether or not a sequence is going to be monotonic increasing or monotonic decreasing by either showing that a sub n is less than or equal to a sub n plus 1 for all n an element of the positive integers, or we can go ahead and show that for f of n, a function that is going to be represented by the sequence generator, so long as the f prime of n is greater than or equal to is greater than 0 for all n an element of the positive integers, then we know that the function which is associated with a sub n is going to be increasing over its entire interval, or we can go ahead and alternatively show that this holds true for all values of n. So notice that it's going to be exactly the same thing here, except for the fact that the inequality sign is in the other direction. And notice that for the first derivative, we have to make sure that the entire function's values are going to be decreasing. In other words, f prime of n is going to be less than 0 for all n. N is an element of z positive. Now, if you take a look at all three of these situations here, all three of these here are going to be increasing, monotonic increasing. All three situations here are all going to be monotonic decreasing. Now, the result that we want to, of course, try to determine is whether or not the sequence diverges or converges. Well, which one of these actually look like they're going to converge or diverge? Well, it looks apparent that this green one is going to diverge, the red one is going to diverge, but it looks like this one actually could possibly converge. In the same respect, when we take a look at the monotonic decreasing sequences, this one of course is going to diverge, this one is diverging, this one looks like it's actually going to converge. So what we can do then is we can actually go ahead and take a look at this important result. It says that a monotonic sequence of real numbers is convergent if and only if it is bounded. Okay, so let's go ahead and determine how do we go ahead and show, once we know that it's monotonic, whether it is in fact bounded. Now, if we take a look at this here, this particular one here, or this particular one here, it is going to be bounded because what's happening is that your second derivative, for this particular case here, is going to be negative. So in other words, what's happening is that it is always increasing, but it is always concave down, which means that it's going to actually have an upper bound. Now, when we go ahead and take a look at this particular case here, this particular case, the function is always going to be decreasing, or the sequence is always going to be decreasing. But if we can go ahead and show that the second derivative is always going to be positive, or in other words, that it's always going to be concave up, then we know as well that this is also going to be bounded on the lower end, and we'll have a lower bound. So, if we can show that it is monotonic increasing, and also show that it is bounded, then what we can do is we can say that the sequence is going to converge for large values of n. And in the same respect for this monotonic decreasing situation. So let's take a look at an example here. Let's say, for example, a sub n is equal to 3 to the n divided by 1 plus 3 to the n. Question again is, does this converge or diverge? Well, very simply, we can just say that the limit as n approaches infinity, if I divide everything by 3 raised to the n, I come out with 1 over 3 to the n plus 1. Of course, if we take the limit as n approaches infinity, then this is going to be equal to 1, and therefore we know that a sub n converges. So this is a very simple example, but what we can do is we can take a look at it from the perspective of it being monotonic, as well as it possibly being concave up or concave down, depending upon whether it's monotonic increasing or decreasing. So let's go ahead and substitute, let's go ahead and associate f of n with the series sequence generator itself, and I'm going to rewrite it as 3 to the n times it by 1 plus 3 to the n to the negative 1, and I take the product rule and I come out with this. And if I take a look at all of these values, for all n being a positive integer, this of course will be a positive value, which means then that it is going to be increasing over the entire value of the domain, and therefore the function itself is monotonic increasing. The sequence is monotonic increasing as well. Now, if we go ahead and take a look at f prime of n and find out what f double prime of n is, here's what f double prime is. And notice that this here is a positive value, positive value, positive value, and this one here is the negative value. So that means that this whole particular function, f double prime of n, is going to be less than 0 for all n being an element of z positive, and therefore it has to be concave down. So what we have is we have this situation. It's always monotonic, it's monotonic increasing, and it is also going to be concave down, which means then that it is bounded, and therefore a monotonic sequence of real numbers, if it is bounded, it is definitely going to be convergent. And that's what we saw just there. Okay, now let's just wrap things up here. Again, what we're trying to determine is whether a monotonic sequence converges or diverges. And if we can go ahead and show that it's monotonic increasing or monotonic decreasing, and then show that it is bounded or not, we can make decisions about the limit as n approaches infinity of the original sequence that we have. Okay, so we'll take a look at a couple of examples again in class, and I'll see you then. Bye-bye.